Have you ever wondered how delivery companies manage to find the shortest route for their deliveries? Picture this. A traveling salesman needs to visit a number of cities, only once each, starting from home, and then return back to the starting point. The catch? The salesman wants to cover the least distance possible. Now this might seem like a simple task, but as the number of cities increases, the possible routes increase exponentially. This makes it a colossal task to find the shortest path. This is not just a theoretical problem, but a real-world challenge that spans disciplines, from logistics to computer science. It's known as the traveling salesman problem, or TSP for short. It's a classic puzzle in the field of combinatorial optimization that has intrigued mathematicians and computer scientists for generations. The question at its core is how to optimize the route. This, my friends, is the heart of the traveling salesman problem. Now this might sound like a simple problem, but it's far from it. The traveling salesman problem, or TSP for short, is actually a classic example of NP-complete problems. What does that mean? Well, NP-completeness is a concept in computational complexity theory. In layman's terms, it refers to problems where finding a solution can be incredibly time-consuming. But once a solution is found, it can be checked quickly. In the case of TSP, as the number of cities increases, the number of possible routes grows exponentially, making it computationally expensive to find the shortest possible route. This is because for every additional city, you have to consider all the new routes that can be formed with this city. In fact, if you had just 40 cities, there would be more possible routes than there are stars in the observable universe. So you see, even a seemingly simple problem can have layers of complexity. So, how do mathematicians and computer scientists tackle such a problem? For smaller instances of the traveling salesman problem, exact solution methods are the go-to. One of these is the branch and bound algorithm. It's like a systematic exploration of all possible solutions, but with a clever twist. Instead of blindly checking every possible route, it branches out to explore promising paths and bounds or cuts off paths that are clearly not optimal. The beauty of this method is that it guarantees finding the shortest possible route. But as you can imagine, even with the smart branching and bounding, the number of potential solutions can quickly get out of hand as we add more cities to our itinerary. That's the drawback of exact algorithms. They're computationally expensive and become impractical as the problem size increases. These methods are perfect for smaller problems, but what about larger ones? For larger problems, we turn to heuristics. Now you may be wondering, what exactly are heuristics? In essence, they are rule-of-thumb strategies that generate solutions quickly. They may not always produce the most optimal solution, but they provide a good approximation, especially when dealing with larger sets of data. Let's take a closer look at the nearest neighbor algorithm. It's quite straightforward, really. Imagine you're a traveling salesman. You start at a randomly selected city and then move to the nearest unvisited city. You repeat this until all cities are visited and then return to your starting point. Simple, isn't it? Another heuristic is the cheapest insertion algorithm. Here you begin with a small subset of cities, then incrementally insert the remaining cities into the subset in such a way that each insertion increases the total travel distance by the smallest possible amount. These heuristics give us a good starting point. But can we do better? Can we improve these solutions? Stay tuned to find out. Enter improvement heuristics. These are the magic tricks in our problem-solving hat, designed to tweak and tune our solutions to the traveling salesman problem, or TSP. While constructive heuristics give us a good starting point, improvement heuristics aim to take these initial solutions and make them even better. Consider the two-opt search, a simple yet effective heuristic. It starts with an initial tour and iteratively replaces two edges with two different edges that decrease the tour's total length. The process repeats until no further improvement is possible. Then we have the three-opt search, a slightly more complex version. It replaces three edges with three different ones, making it a bit more aggressive in its search for an optimal solution. These heuristics, while not always leading to the absolute shortest path, often provide a significantly improved tour compared to the initial solution. But what if we want guarantees on how good our solution is? This is where approximation algorithms come in. As we journey deeper into the world of the traveling salesman problem, we encounter a realm of near solutions, a universe of almost there answers. These are the approximation algorithms. Rather than seeking the absolute shortest path, these algorithms aim to find a path that's short enough. One such algorithm is the minimum convex hull algorithm. Imagine wrapping a rubber band around the outermost cities. This forms your initial path. Now, Iteratively add cities within this path, always ensuring you generate the smallest possible increase in the total path length. This approach offers a certain guarantee: your solution will never be more than twice as long as the optimal solution. In the complex landscape of the traveling salesman problem, this is a comforting assurance. So we've seen how approximation algorithms offer a practical approach to tackling this problem. But the traveling salesman problem isn't always symmetric. Sometimes the distance between two cities isn't the same in both directions. Now, this might sound like a riddle, but it's actually a twist on our traveling salesman problem known as the asymmetric traveling salesman problem, or ATSP. In the classic TSP, we assume that the distance from city A to city B is the same as the distance from city B to city A. This is called triangular symmetry. But the real world isn't always so neat and tidy. Maybe there's a one-way street or a mountain pass, or heavy traffic that makes the return trip longer. That's when we encounter ATSP, where the distances between cities don't follow this symmetry. It adds another layer of complexity to the problem and requires different strategies to solve. So while ATSP may be a bit more challenging, it's also a bit more realistic. But what if the cities are in Euclidean space? Euclidean graphs allow for specific techniques for resolution. Now let's delve into how the traveling salesman problem, or TSP, is approached when cities are located in Euclidean space. In a Euclidean graph, cities are represented as points in a two-dimensional plane, and the distance between any two cities is the straight-line distance between them. This is a reflection of our physical reality, where we often need to find the shortest path between locations in a two-dimensional space, such as a map. In this context, the TSP is solved using algorithms that exploit the properties of Euclidean space. For instance, the Delaunay triangulation, or the minimum spanning tree, can serve as a starting point for constructing a tour. These methods leverage the geometric properties of the city's locations to efficiently approximate solutions. Remember that while Euclidean TSP is a special case, it is still an NP-hard problem, and finding the exact shortest tour can be computationally challenging. From abstract to practical, the traveling salesman problem has many real-world applications. From planning delivery routes to designing electronic circuits, TSP has a wide range of uses. The practical applications of the traveling salesman problem extend far and wide. Let's start with delivery routing. Consider a mail carrier who needs to deliver mail to various locations in a city. The TSP can help determine the shortest route to visit each location once and return to the starting point, minimizing time and fuel costs. In the world of electronics, TSP comes into play in circuit board manufacturing. The problem can help define the most efficient path for a drill that makes holes in the circuit board. Ever heard of laser cutting machines? Well, they too make use of TSP. These machines are used to cut materials into specific shapes. The TSP can help determine the most efficient path for the laser to follow, reducing the total cutting time. These are just a few examples of how TSP is applied in the real world, and the field is still evolving. Innovation never stops in the world of mathematics and computer science. The traveling salesman problem, a long-standing puzzle, has seen fascinating advancements in recent years. The quest for the optimal solution has led researchers down new paths, exploring innovative techniques such as genetic algorithms and machine learning. Genetic algorithms mimic the process of natural selection, where the fittest individuals are selected for reproduction to produce the offspring of the next generation. In the context of the traveling salesman problem, genetic algorithms can be used to optimize the route, producing increasingly efficient solutions over generations. On the other hand, machine learning algorithms learn from the data and improve over time without being explicitly programmed. They can be trained on numerous instances of the problem, learning to identify patterns and make predictions for new unseen instances. These cutting-edge techniques are reshaping how we approach this age-old problem. So next time when you receive a package, remember the complex math that might have helped it get to you.